Okay? Okay, we're ready.
Okay, thanks. Okay, so first I'll just do a quick revision of the analysis of circuits using Laplace transform. So just a simple example. So if you're given the following circuit, this is our voltage supply, which is given as 10 U of t. Okay, then we have an inductor with 1 Henry is the notation, then 3 ohms resistor and half farad capacitor. Okay, and the current goes out from the positive side and comes into the negative side as usual from circuit theory. It's denoted by I of t. This is time domain. The first step is to write the corresponding S domain circuit, right? So in S domain, we will just take the Laplace transform of 10 U of t. What would that Laplace transform be?
10 over.
Correct, 10 over S. And our inductor will be represented by, any ideas? Only S. So everything becomes a resistive component in S domain, okay? And our resistor is just represented by 3, and our capacitor is represented by 2 over S, okay? And our current will now be represented by I of S, okay? So just to point out, our voltage supplies V of t and current I of t transform to V of S and I of S. Our resistor remains the same, you just get the resistor value. Our inductor changes to S, and our capacitor L of S to be correct, and our capacitor changes over to 1 over C. Okay, so these are the basic equivalents of our circuit components in the S domain. So to find I of S, our next goal is to find I of S. So we will use the circuit theory equation of voltage is equals to product of current and our impedance, which is represented by Z of S right now. Okay, now this Z of S is just a sum of these 3 components because they're connected in series and all of them are resistive. So you have S plus 3 plus 2 over S. Okay, this is equals to S square plus 3S plus 2 over S. Okay, and our Vs is equals to 10 over S. That's what we had just found. All right. Okay. So now I of S is just V of S over Z of S, which will give us 10 over S square plus 3S plus 2. Now we'll continue with our standard method of partial fraction expansion. All right, and this will give us 10 over S plus 1 minus 10 over S plus 2. Take the inverse of this expression and we'll get our I of t to be 10 e raised to the power minus t minus e raised to the power minus 2t u of t. Let me zoom in. Okay, any questions on this? Standard form. So whenever you have a circuit given to you, first step is to convert it to S domain and then solve in S domain. All right, shall I move on? Okay, so next thing is how would you realize a system if it's h of s is given to you. So 1 second. So we have cascade and parallel realization. Okay, so if h of s is given, for example, to be 4s plus 28 over s square plus 6x s plus 5. Okay, now this can be written as, the denominator can be factorized to s plus 1 and s plus 5, right? So in cascade, we will write it as 4s plus 28 over s plus 1 multiplied 1 over s plus 5. Okay, so this is my first system, that is h1 of s, and this is my second system, that is h2 of s. I can do it the other way around also. I can write it as 1 over s plus 1 and 4s plus 28 over s plus 5. So this will be h1s right now, and this will be h2s. Okay, either way. This is our cascade realization, wherein, if in block diagram terms, if we see it, first I'll have h1 of s followed by h2 of s. Right? How does this follow? So in time domain, this will be convolution of h1 with h2, and in s domain, it's the multiplication of these two. Okay? So a cascade is represented by multiplication of two systems in s domain. All right? We can do a parallel realization of the same thing. So for parallel realization, we will go on with partial fraction expansion. So if the same system is given to us, its partial fraction expansion is 6 over s plus 1 minus 2 over s plus 5. So now 6 over s plus 1 is my first system, that is h1s, and 2 over s plus 5 is my second system, that is h2 of s. Okay, so my parallel realization now looks like this: h1 of s, h2 of s, and then a summation. So x of s is my input, y of s is my output. Okay, and here's a plus and here's a minus sign because of this minus sign over here. All right, so the same system can be realized in cascade or in parallel form. Okay, any guesses on what would be the advantage of a parallel form over a cascade form? So in parallel form, our computation could be faster because both of these will be computed at the same time, whereas the computation of h2 of s depends on h1 of s. Okay? So that's just a side note on realization. And now I'll just move on to our Z transform topic. Okay? So Laplace was for continuous time signals. Laplace transform. And Z transform is for discrete time signals. All right. Do note that even when we take the Z transform of a discrete time signal, the Z transform itself is continuous. Okay, the Z transform is not discrete. So the definition is, again, you have a unilateral and bilateral Z transform. Okay, bilateral Z transform runs from minus infinity to infinity second, x of n z raised to power minus n. Do note that n only takes integer values, it's not continuous. Okay? If it would have been continuous, we would have taken an integration. Alright? Because it's discrete, there's a summation over here. Okay? So be careful of that n only takes integer values. Okay? And unilateral, just like Laplace transform, runs from n is equals to 0 to infinity. Alright? Now our inverse Z transform will be similar to the Laplace transform. Okay, and there's an integration over here because x of z is continuous. Okay, x of z is non-discrete. All right. I'll just quickly, yeah. Sorry. Okay, I'll just do quickly an example that I think has been covered in class, but just want to reinforce some things. So the first thing, again, just like Laplace transform, is an expression is given to you and you're supposed to find the Z transform and the ROC. ROC is again the region of convergence. So this is example 5.1 from your textbook. Okay, so if it's given that x of n is gamma raised to power n u of n. Okay, so what does gamma look like? And gamma is less than 1. So the value of gamma is less than 1. So our x of n will look like this. It's a decaying exponential. Okay, and this only occurs at integer values of n and so on. All right. Now, if you're supposed to take the Laplace transform of this function, let's just substitute it into the formula. So our x of z will now be summation of from n equal to 0 to infinity x of n z raised to power minus n, and we'll just substitute x of n, so we'll have gamma n z raised to power minus n. Okay, because u of n is 1 for n equal to 0 and any value greater than that, right? So this comes down to gamma over z raised to power n, right? And this looks like what sort of a series? Correct. And what is the common ratio that we are multiplying with? Correct. So our common ratio is gamma over z, and it's a geometric series. Is it a finite geometric series or an infinite geometric series? Sorry? Depends on what? No. It's an infinite because our n is going up to infinity. Okay, so if n was up till a value, say 10, it's from 0 to 10, then it's a finite geometric series. Okay, if n are the argument in this case is going up till infinity, then it's an infinite geometric series. Okay, so it's an infinite geometric series. All right, so if it's an infinite geometric series, we have a formula for the sum. So for example, this is a geometric series 1 plus x plus x plus x cube and so on. The sum is given by 1 over 1 minus x, right? If this is less than 1. So x here is a common ratio. Alright, so again this is a geometric series, so x of z will just be a sum. So applying this formula, we'll have 1 over 1 minus gamma z, and this is when gamma over z absolute value is less than 1. Okay, just simplifying this expression, we'll have z greater than gamma. Alright, so what does this condition denote for us? This is our ROC, region of convergence. If this condition is not met, our x of z is not a finite value. Okay, so region of convergence means the values of z for which our x of z is a finite value. It converges to some value, it's not infinite. Okay, so if we are supposed to plot this value of this ROC, what will it look like? Any guesses? So we will have a circle of radius gamma, and anything outside this circle will be our region of convergence. Okay, because our condition is absolute value z should be greater than absolute value of gamma. Oops, sorry. All right, all clear? Okay. Now, again, just like Laplace transform pairs, there are a lot of z transform pairs already given to you. There's a table in the textbook. It's a good idea to go back and practice these, how we get these transform pairs. I'll do another example for you. So let x of n now be, this is example 5.2 part C. So x of n is now cos beta n u of n. All right. Now, how can we write cos beta n as exponentials? So a quick trick is, since our z transform formula has this raised to power n, z raised to power n, it's a good idea if we transform our x of n to be exponentials. It will be easier for us. All right. So how will you write cos beta n as exponentials? Correct. So cos beta n is e raised to power j beta n plus e raised to power minus j beta n over 2. Standard Euler's identity. All right. So my x of n is now e raised to power j beta n plus e raised to power minus j beta n u of n. Okay. Now my x of z will be n equals 0 to infinity. I can take my half outside, keep it as a constant, and I'll have e raised to power j beta n zn plus half summation n equal to 0 to infinity e raised to minus j beta n z of n. Okay. Now, this term e raised to power j beta n is equivalent to gamma raised to power n when gamma is equals to e raised to power j beta. Correct. So just using the formula from the previous example, right from the previous example, we will have half z over z minus e raised to power j beta plus z over z minus e raised to minus j beta. Any questions on this? And for this to happen, my absolute value of z again has to be greater than absolute value of gamma, and gamma in this case is e raised to power j beta plus minus, right? And what is this value? 1, correct. How is this 1? my e raised to power j beta is equals to cos beta plus j sine beta, and absolute value of e raised to power j beta is equals to under root cos square beta plus sine square beta. This is 1 always for any value of beta, so it's 1. Alright, so absolute value of z greater than 1. Okay, we can simplify this further if you want to. So this term will finally look like z into z minus cos beta over z square minus 2z cos beta plus 1. Alright? Okay. Any questions on this? Cool. Now the next thing to do is inverse z transforms. Okay, so let's start with that. So inverse z transform is pretty much similar to the Laplace transform that you were doing. The technique we were using, again, the partial fraction expansion, and again using the tables to get our transform pairs. Let me just pull up the example for you. So it's given to us that x of z is 8z minus 19 over z minus 2 into z minus 3. Okay. Now, if we go on and do a partial fraction expansion on this, okay, we will get 3 over z minus 2 plus 5 over z minus 3. Sorry. Okay, and using the transform pairs, so the transform pair I'll just list down. 1 over z minus gamma results in gamma raised to power n minus 1 u of n minus. This is the transform pair I'm using. Okay. Now using this transform pair, what will you get as x of n? Three times 3 times 1. What 1? Using this transform pair that I've just written. Use this formula.
A is due to 1, but it's due to 0, which is 1.
No. So it's 3 times 2 raised to power n minus 1 u of n minus 1 plus 5 3 raised to power n minus 1 u of n minus 1. Okay? Yeah.
What if you factored out a 2 on the top, but in the numerator at the very beginning?
Why would you do that?
Because that gives you z minus 2 over z minus 2.
It gives you z minus 2?
Like, if you have... I misread that.
It's 8z minus 19. Okay. All right.
I wrote down 16.
It's okay. Okay. So one issue with this technique is that you will always get your answer in n minus 1 terms. Okay, which is not something that we want. So if we have one second. If we take the partial fraction expansion of this term, we will not get these n minus 1 terms, because whenever, if you see, whenever there is a u of n term in our x of n, so in the table, this is my discrete in table 5.1 specifically, these are my discrete signals and this is my Z transform. Whenever my x of n is multiplied with u of n, I have a Z in the numerator. Alright? That's why we'll be dividing by 0 and then multiplying with Z later. Okay? So for Z transforms, whenever you're taking the inverse Z transform, you will always do the partial fraction expansion of xz over z, not of xz directly. Okay? Just to get rid of this n minus 1 factor. Okay? And get it in terms of n only. Alright? So just be careful with that always. So now, let's come back to the example. xz over z will now be 8z minus 19 over z, z minus 2, z minus 3, correct? And now do the partial fraction expansion. Okay, now this will give us minus 19 over 6 over z plus 3 over 2 over z minus 2 plus 5 over 3 over z minus 3. Okay, and now we will multiply both sides with z. Alright, so we'll get xz back. We'll have minus 19 over 6 plus 3 by 2 z over z minus 2 plus 5 over 3 z over z minus 3. Now x of n from the table will now be minus 19 over 6 delta n. So just like Laplace, a constant would have a delta inverse. Okay, so in Laplace, whenever you had a constant, you had a delta t. In Z transform, whenever you have a constant, you have a delta n. Alright, and now our answer will be 3 over 2, 2 raised to power n, plus 5 over 3, 3 raised to power n, u of n. Okay, so whenever taking the inverse Laplace transform, inverse Z transform, you'll always do the partial fraction expansion of xz over z. Okay, and once you've divided by z, do not forget to multiply with z again after the partial fraction expansion. All right. Okay, so in this case, what sort of roots do we have in this case? Are they correct, real, distinct? So this is the case of real, distinct roots. All right. Similarly, like in Laplace, we can have repeated roots and complex roots as well. Okay, so let's do an example with the repeated roots. And by roots, I also mean poles over here. So the roots of the denominator are poles. All right. And what are the roots of the numerator called? Correct. Okay. Now let's do an example for this. So x of z is given to be, I don't like this example. Z 2z square minus 11z plus 12 over z minus 1 z minus 2 cube. Okay, so the poles that we have are, one is at 1 and there are 3 repeated poles at 2. Alright, again we will do the partial fraction expansion of xz over z. Okay, now our partial fraction expansion will look like k1 over z minus 1 plus k2 over z minus 2 plus k3 over z minus 2 squared plus k4 over z minus 2 cubed. Correct? Now k1 and k4 can just be found out by multiplying xz over z with z minus 1 and z minus 2 cube respectively and substituting z equal to 1 and z equal to 2. So in this case, multiply by z minus 1 and substitute z is equals to 1, and in this case multiply by z minus 2 cube and substitute z is equals to 2. Okay, the standard format. Alright, and then for k2 and k3 we'll take the derivative. Okay, so for k2 and k3 take derivative and then substitute. Okay, now through this method we'll have k1 equal to minus 3, k2 equal to 3, k3 equal to minus 1 and k4 equal to minus 2. Okay, now from the z transform table again, we will have that z over z minus gamma raised to power m plus 1. Since we have powers over here, for these, our inverse looks like n minus 1 up till n minus m plus 1 over gamma raised to power m factorial gamma raised to power n u of n. Okay, and this is again given in the table, so you don't have to really worry about this. Okay, all right, so once that is done, our x of n, so I'll just write x of z once, minus 3 over z minus 1 plus 3 over z minus 2 minus 1 over z minus 2 squared minus 2 over z minus 2 cubed. Again, multiply with z and then use the transform table. Okay, so we will get x of n to be minus 3 u of n plus 3 2 raised to power n u of n minus n over 2 into 1 factorial into 2 raised to power n u of n minus 2 into n minus 1 over 2 squared into 2 factorial 2 raised to power n u of n. Sorry. Okay, these two again come from this condition. What? Yes. So first you have to multiply by z. I didn't write it. That's xz over z right now. You have to multiply this expression with z and then take the transform.
So how come it's negative 3
1 second. Negative 3 u of n. Z over z minus 1. That's what you'll get, right? Z over z minus. Yeah, there has to be a 1 raised to power n. Okay. It is assumed that since n is from 0 to infinity, this will always be 1. So it doesn't really matter. All right. So that's the case with repeated roots. And then let's do another case with complex poles. Everyone got this? Yeah, okay. Okay, so now complex roots. Okay, so now in our case xz is now 2z 3z plus 17 over z minus 1 z square minus 6z plus 25. Okay, so the poles now are z1 is equals to 1, z2 is equals to 3 plus 4j, z3 is equals, again, z2, 3 minus 4j. Again, the complex roots will always be complex conjugates of each other. Okay, so roots will be complex conjugates. All right. Now, again, we'll do a partial fraction expansion of xz over z, which will be k1 over z minus 1, k2 over z minus 3 minus 4j, and k2 conjugate over z minus 3 plus 4j. And k2 will be again complex conjugates. Okay, so you just have to find one term and the other will be the complex conjugate of the other. All right. Now, again, using a standard method, k1 will come out to be 2, k2 will come out to be 1.6 e raised to the power minus j 2.246, and k2 conjugate, you'll just calculate from this term. You don't have to actually substitute the value. J 2.246. All right. Now, substituting this back into our original equation, you'll have 2 over z minus 1 plus 1.6 e raised to power j minus 2.246 over z minus 3 minus 4j plus 1.6 e raised to power j 2.246 over z minus 3 plus 4j. Okay, and then using our z trans, again multiply with z and then use z transform table. All right, we will get xn to be 2 u of n, or this can be written as 2 1 raised to power n u of n. This will always be 1 since n is greater than or equal to 0. All right, and the other term will come out to be this. Okay, so this term comes from our 3 plus 4j. This term comes from our coefficient, numerator coefficient. 5 raised to power n is the absolute value of our pole. All right, and this is just the double of our 1.6. Okay, so you will see the relation in the table. So I'll just write down that for you. One second. So it's in the table, it's the pair 12b. That says it's R, absolute value of gamma n cos gamma n plus theta u of n, and this has a transform pair of 0.5 r e raised to power j theta z over z minus gamma plus 0.5 r e raised to power minus j theta z over z minus gamma conjugate. Sorry. So this term here matches this term. Okay? Any questions? Okay. Let me do a little demo in MATLAB for you guys. Okay. So, 1 second. Yeah.
Part before the absolute value general
R.
is that like greater or this?
R is just a constant. Yeah. So over there, here we have 1.6. That's what R is.
Oh, okay.
Okay. So
Base R squared?
no. So 1.6 is 0.5 into R. Okay, so R will be 3.2. Okay, so that's where you get this from. Make sense? Okay. Yeah. So Z-trans is a MATLAB function. Okay, so let's try a few of these examples. So sims is a command that defines symbols in your MATLAB program system. So now k and x are defined as symbols. They're not variables. Okay, so you can actually write functions and expressions using these. Okay, you can't write functions and expressions essentially using variables. Sometimes you can probably. And now let's define our, so this is our discrete time function now. Okay, so with the variable, if k was a variable, we couldn't have done this without defining the values of k. Okay, but since k is a symbol now, we can do this. All right, And for Z trans, we just have to give, so F is my Z domain variable, var is my index, which was n in our case, so it's k over here, and x is the trans var. Okay, so instead of z, I'm getting x over here. Alright, so if we look back to our Z transform pairs and look at, if I can find it out, here. So we'll have Z sine beta, and sine beta is nothing, beta is 1 over here, that's why it's sine of 1, okay. Then Z is again x over there, so it's x squared 2 cos x plus 1, okay, because gamma is also 1 over here in our case. Alright, so that's one thing that you can play with, Z trans. And that's it for today, I think. Thanks, Andrew.
Is this room going to be locked? Sorry? Is this room going to be locked? How can we leave?
At least not till 2:30. After that, it probably will be.
Just wondering.
Until 2:30, we have access to this room.
Yeah, I don't want to stay too late and then,
Get hugged.
yeah.
Right. So he says that the table has this one. And the 0.5 cosine. Wait, I thought gamma variables. So gamma over here is for this. This thing is gamma. Okay. So okay, yeah. So gamma would be the variables protein. Yeah. So gamma is 3 plus protein, and this is gamma contributed. Okay, so basically you multiply by 2. And would this be on the table too? This is so this thing that is in between, and that's what only for the upper C. This has nothing to do with this equation. Okay, so it's a square. But that's how you know that it's going to be. So basically you just simplify. You just cross multiply. Where did the half? Oh, the half one comes from. How comes from the Lewis identity? Yeah, yeah. But then, yeah. Sorry for the first 5 minutes. Okay. I got all the way up to like the H1s, H2s. Yeah. Oh, it's straight from here. Yeah. So this is Cascade. So this is Cascade, and this is that. Same system. And you separate it. And then, so can I do it like this or like this? Okay. Like this thing can be written like this or this? Okay. So an H1 and H2 is going to be either of these two. Oh, so you don't partial fraction. No, the partial fraction is only when you do binomial equation. Okay. Two options. Yeah, that's right. Oh, it is partial. Yeah, it is partial. Okay. You want me to understand? And so for the first part, analysis of circuits, this was just a division of what we found in class. Is the just a division? Could I write that down? Yeah, sure, sure, sure. So I was like trying to do the homework, and then I was like, oh, I should do the exam. But I was just too tired, so I didn't. Which is a terrible excuse. What happened to your hand? Oh. Did you go kayaking and no. So we have this side table which is a glass top, and the router sits on the table. And 1 month ago, I like connected my router through the LAN cable to my laptop. And very happily, I was just roaming around with the laptop, and the router fell on the table, and it just nicked one of the edges. So yesterday, day before yesterday, I was picking up something very close to the table, just scratched myself. You knew about this. You were the one who did this. Instead, you were the one who scratched it. That's very managed. It's okay if someone else had broken it and I didn't know about it, then it's fine. It's like you sort of have responsibility. Yeah. Like, oh my god, I am the one who did this. Genius. Smart. It's like me, I think I spilled water on the floor. I meant to clean it, but I was like, no, I'll just let it dry. And then I walked over and I slipped, and then I'm like, wow. Why? I knew it was there. I knew it was there. It's like it was punishing you for being lazy or something. And then my friend yesterday said, wrong side. You're supposed to cut yourself on this side. You're like, dude, I'm not killing myself.
Right, right.
As long as you want me dead, I know